Welcome my dear learners for this course on design of machine elements 1. In this module 1 we were discussing on stress concentration. So far we have solved 5 numerical problems on stress concentration. Let us continue our discussion. The problem number 6 of our discussion on stress concentration states that a grooved shaft shown in figure 6 is to transmit 5 kilowatts at 120 rpm. Determine the diameter of the shaft at the groove if it is made of C15 steel with sigma yield 235.4 megapascal. Factor of safety is 2. Let us solve this problem. If we move for solution of problem number 6 of our discussion, before that if I list out the data given, we have the shaft is to transmit 5 kilowatts at a rated speed of 120 rpm. And we have sigma yield which is given as 235.4 megapascals with factor of safety is 2. Now to determine the stress concentration factor or the diameter, we want torque. Torque is missing. How much torque? He has not specified, but he has specified power and rpm, thereby I can find out how much is the torque. Now through the visual inspection itself, since power and rpm is known, I can find what is the torque by the general relation P is equal to 2 pi nt by 60,000. So therefore let me determine the torque first. That is, we know that power is equal to 2 pi nt by 60,000 for kilowatts. So power is 5 kilowatts, hence it is 5 2 into pi into 120 into torque divided by 60,000. So I will get how much is the torque transmitted. It is 5 into 60,000 divided by 2 into pi into 120. Therefore the torque transmitted is 397.887 Newton meters. Hence in terms of millimeters it is 397.887.4 Newton mm, because we know that from Newton meter to Newton millimeter we should multiply 10 power plus 3. So multiplying 10 power plus 3, I will get the answer as 397,887.4 Newton millimeters. Now he is asking to determine the diameter of the shaft at the groove. What he specified D, he is asking us to find out the D. Hence, as we all know that whenever there is a change in cross section or geometric dissimilarities, there are stress risers which contributes for accumulation of maximum stress, which is termed as stress concentration, which can be solved by comparing the given sketch to these figures between 2.11 to 2.30. Therefore, if I compare this sketch to these figures, I found out that the figure 2.22 of page number 41 is grooved shaft subjected for torsion, grooved shaft in torsion. So comparing it, I found out that figure 2.22 is what similarizes the given problem. So therefore if I observe this graph, we have the ratio of R by D, D by D and stress concentration. X-axis is R by D, Y-axis is stress concentration factor Kt, and curves of D by D is also presented. So R by D is found to be 0.1. So mark 0.1 because radius is 0.1 D divided by D, dd will get cancelled. I will get R by D as 0.1. Capital D is 1.1 D, small d is D, so dd will get cancelled. I will get 1.1 as the D by D ratio. D by D ratio is 1.1 curve. So if I move up, intersect 1.1 curve and come horizontally towards left, I found out that the stress concentration factor is found to be 1.475. 1.475. It lies exactly between 1.45 and 1.5, hence I can take it as 1.475. So now we know that stress concentration factor Kt is equal to tau max by tau nominal, because it is torsional shear stress. Now he has specified the value of normal yield strength. We know that tau max is equal to tau yield by factor of safety. Now tau yield is unknown for us. Now tau yield is equal to sigma yield by 2. So this one should know, which is very important. So therefore tau max will become sigma yield by 2n, 2 times the factor of safety. Sigma yield is 235.4 divided by 2 into factor of safety is 2. So therefore tau max will be how much? Tau max will be 235.4 by 4, which is turning out to be 58.85 megapascals. Kindly make a note. Tau yield is half of sigma yield. So tau max is tau yield by factor of safety. So therefore substituting it, I will get tau max as normal yield strength by 2 times factor of safety. So I got tau max, and we know Kt. Now I can find how much is the tau nominal. So therefore nominal shear stress is given by tau max by stress concentration factor. Hence nominal yield stress will become 58.85 divided by 1.475, which is 39.9 megapascals. Now for torsional stress, we know that tau nominal is equal to T by J into R, or which is also written as T by Zp. Zp stands for polar section modulus. Polar section modulus is given in figure 2.22. So polar section modulus Zp is given in figure 2.22. Zp is equal to pi d cube by 16. This is from figure 2.22 directly. So therefore we know tau nominal, which is 39.9. We know torque. So if I substitute, I will get 16 times torque is 397887.4 divided by pi d cube. Hence I will get the diameter d as, let me write it here itself. Hence the answer d in millimeters will be 16 into torque is 397,887.4 divided by pi into 39.9 cube root of answer, which is 37.03 mm. 37.03 millimeters. So this is the diameter of the shaft for problem number 6. This is how you should solve for torsional shear stress problem considering stress concentration. Let us quickly move and solve problem number 7 also. If I move for solution of problem number 7, we have a shaft of 50 mm diameter is stepped down to 40 mm with a fillet radius of 5 mm. If the allowable shear stress is 50 megapascals, determine the power that can be transmitted at 1200 rpm. So he is asking us to determine what is the maximum power that can be transmitted. To determine power, I want torque. Torque is missing here. So therefore if I find torque, I can find how much is the power transmitted. So now if I move for solution of problem number 7, we have the data specified as the shaft diameter capital D is 50 mm, small d is 40 mm, and fillet radius R is 5 mm, and we want to determine power for a rated speed of 1200 rpm. Find the power by considering stress concentration is asking us. Now find tau nominal first. We have specified tau max is 50 megapascals. So if I find stress concentration factor, I can find how much is the tau nominal. So therefore, if I compare this sketch, I will get from data handbook, we will get from figure 2.27, from figure 2.27 referring to page number 44, referring to page number 44, figure 2.27 is stepped shaft in torsion. Stepped shaft in torsion. Now if I look at that graph, we have R by D and D by D curves. If I find R by D, I will get the value as 5 divided by 40. 5 by 40 will be 0.125, and we have capital D by small d, which is 50 by 40, which will be 1.25. 50 by 40, which is 1.25. So mark R by D as 0.125. Move ahead between the lines of 1.02 and 1.5. So move between these two, mark a point and come horizontally towards left. You will find out that the value of stress concentration factor Kt is turning out to be 1.31. 1.31. So now as usual we can solve. We have found out Kt. Kt is tau max by tau nominal. Tau max is known, so therefore tau nominal will become, tau max is specified as the maximum allowable stress is 50 megapascals. 50 divided by 1.31. Tau max is given. It is data. Hence I will get tau nominal as 50 divided by 1.31, which is turning out to be 38.17. 38.17 megapascals. Now we know that tau nominal is equal to T by Zp, that is polar section modulus. Polar section modulus is specified in figure 2.27. So Zp is equal to pi d cube by 16. It is specified in the same figure where we took the stress concentration factor. So tau nominal is known, Zp is also known. I can find how much is the torque, that is 38.17 is equal to 16 into torque divided by pi times 40 cube. Pi times 40 cube. Hence torque will be 38.17 into pi into 40 cube divided by 16. So therefore torque is turning out to be 479658.36 Newton mm. Hence torque is equal to 479.658.4 Newton meters. Now I can find power. P is equal to 2 pi nt by 60,000 kilowatts. So hence power is 2 into pi into 1200 into 479.6584 divided by 60,000. Hence power transmitted in kilowatts will be 2 into pi into 1200 into torque is 479.658 divided by 60,000. It is 60.28 kilowatts. So power transmitted is 60.28 kilowatts. This is how we should solve problems on shafts subjected for torsional shear stress with stress concentration factor taken into account. That's all from this lecture. Thank you all.